Okay, so welcome back to the class of CEMS 446, Mechanics of Composites. So today we're going to talk about the macro-mechanical analysis of lamina. So in the previous few lectures, we covered this macro mechanics of composites. So actually, for this really common composite, there's one type of composite that is called laminated fibrous composites that is made by bonding together two or more lamina so that you can get the desired properties of the laminate. And this is different from sheet laminates made by bonding flat sheet of materials, because in this laminate, you use a lamina which is which have anisotropic properties, right? Physical properties, because of the unidirectional fibrous reinforcement. So with that macromechanical analysis of fibrous composites, we found out this. We can calculate this physical properties of lamina, and it's really useful to analyze the composite behavior and by the macromechanics analysis of a thin unidirectional lamina. And then if we want to study a lamina, which is the a laminate, if we want to study the laminate, which is constructed by stacking the those lamina in the direction of lamina thickness, we want to find out the mechanical properties of those laminate, right? And that's really important, because we're going to use those laminates as the built-in structure to make other functional devices. So, for example, these mechanical structures made of these laminates, such as leaf spring suspension system in the automobile, usually a truck, are subjected to various loads, such as bending and twisting. So we need to find out how these laminates behave under those mechanical loading. So this is a typical laminate made of 3 lamina. You see we have 3 lamina for each layer thickness. And you can arrange at whatever direction based on your design of the laminate. And with different alignment of this direction, you will get different overall physical properties of your laminate, even though for each lamina you have the same physical properties. So the stiffness of the lamina varies from point to point, right? So if you have a really sharp tip to touch the surface of a lamina, and you will, it depends on whether you touch the fiber area or the matrix area or the fiber matrix interface, you have huge difference in the physical properties, right? Such as the stiffness. So accounting for those variations will make your calculation or mechanical modeling of the lamina very, very complicated. Right? Imagine for one lamina, you have numerous fibers aligned in the matrix, right? And if you want to have a model to show to calculate that many fibers and matrix in the laminate, the calculation model, will be extremely hard to run, because you have to deal with those independent fiber, and each fiber have its behavior under the mechanical loading. So for this reason, you want to simplify your model to analyze your lamina, right? Sorry, you want a simplified model to analyze your laminate, right? Based on your lamina. So for this reason, the macromechanical analysis of a lamina is based on the average properties and considering the lamina to be homogeneous. So based on that lamina, you can model the laminate, right? So apparently that's the assumption, right? You just assume this lamina, your lamina is homogeneous. They have the average properties that is calculated based on your macromechanical analysis. So, but even with the homogenization of your lamina, the mechanical behavior is still different from the homogeneous isotropic material, right? So from the Ruhr mixture and based on the macromechanical analysis, you can find out those physical properties in two directions, right? It is direction dependent. So for example, the Young's modulus along the axis direction or perpendicular to the axis direction, they're vastly different, right? So they're not isotropic material, they're just homogeneous, but not isotropic. Okay. So what is the isotropic material, right? So if this is if there's the object, which is the isotropic material made by isotropic material, you put a load on the object at one direction, the direction 1, which is the case A, right? And the other case is when you apply force or load in the 2 direction. Therefore, of course, you have this deformation in the 2 direction, right? But based on the Boston ratio, you also have a deformation in another direction. So here, with the load in the 1 direction, you have the deformation delta 1A, right? A is the case A. Of course, you have the deformation delta 2A. This delta 2A, the negative. No, sorry. This is delta 2A. So I think this is a bit problem here. One direction, right? So this is 1 direction. This is 2 direction. And you apply force in the 1 direction. This is 1A, right? This is 1 direction. This is 2A, right? This is 2A. So this is 1B. This is 2B, right? Right. So apparently this delta 2A is a negative value, right? Well, here delta 1B is a negative value. So if you have a isotropic material, you will find out when you apply the same amount of loading and on the 2 directions, you will find out the delta 1A equals to delta 1B. No, sorry, this is actually, this is correct. Yeah, so delta 1A equals to delta 1B, right? Delta 1A equals to delta 2B. Delta 2A equals to delta 1B, right? That makes sense, right? All right, so this is the case for the isotopic material. You'll see that whenever it doesn't matter which direction you apply the load, right? You will have the same deformation for the isotopic material. If you have those unidirectional lamina, let's see how it deforms for this unidirectional lamina. Right? For example, we have this this kind of model, and you have fiber across in the one direction. Right? So this is the fiber direction, and two is apparently is the transverse direction. Right? One is the longitudinal direction. And we want to apply the load in the one direction and or the two directions to see how it deforms. Right? So the width, the size of this object is W by W. So if you, for the case one, case A, when you apply the force in the one direction, right, with the load P, of course, you will also have the deformation that the 1A this is delta 1A, okay, delta 2A, delta 2B, delta 1B, okay. So if we know that the Young's modules in those two directions are different, right? Usually the Young's modules in the one direction is much higher than Young's modules in the two direction, right? So you can imagine that the delta 1A here, this should be delta 1A, delta 1A here should be much smaller than delta 1B, right? This one should be much smaller than this one, right? And the other deformation, you have to calculate this based on the Boston ratio of this unidirectional lamina, right? Then you can find out the deformation in the other direction. And apparently the Boston ratio, because of the Boston ratio, you will also have a different value in another direction, right? So for those unidirectional lamina, the deformation will not be the same when you apply the force in two directions. So in this case, the deformation of a unidirectional lamina is direction dependent, right? So what's the case if you apply force that is not parallel to the, not in the direction one or in the direction two, right? Or in the longitudinal direction or transverse direction. When you have an angle applied, when the force have an angle applied to the longitudinal direction. So in this way, you will have this shearing deformation, right? In addition to your normal deformation. So in this case, you will this square shape becomes a twisted one, right? So let's have a review of the stress and strain and how you calculate stress and strain, right? Especially in 3D space. Right? Let's start with the 2D. So really basic one on the normal stress, right? Stress by definition is the force over area, right? So if you take a small area of force, if you take a small area, of course you have this force applied to that small area, right? Delta px. You know, if you have the want to calculate the stress in the x direction, right? Take this really small area, and that be delta px over delta a. Delta a is the area, and when the delta a approach to 0, you will have the stress, normal stress in the x direction as almost to calculate to the point, right? And for the shear stress, tau xy, shear stress xy, it's actually when calculated based on the force in the y direction, right? So the delta A, the area, is parallel. The delta A, the area is perpendicular to the x direction, right? So the delta A, the area is in the plane of xy. No, in the plane of yz, right? The delta A is in the plane of yz, perpendicular to the x direction. So the tau xy is the force in the y direction that is applied to the plane that's perpendicular to the x direction. Okay, and the other the other shear stress, which is xz, is the force in the z direction applied to this limited area that is perpendicular to the x direction. Okay, so you have two different kind of shear stress. Similar to this, you can find out the normal stress in the y direction, right? Normal stress in the y direction, normal stress in the z direction, right? And also you get the shear stress yx, the shear stress yz, shear stress zx, and shear stress zx, right? Similar way. In that case, the delta A, this aerial plane, will change, right? The delta A here is perpendicular to the x-axis direction. So the delta A here should be perpendicular to the y-axis direction, right? So usually this shear stress xy should be equal to shear stress yx. Shear stress yz equals to shear stress zy. Shear stress zx equals to shear stress xz. So how many we have? 6 here. It says we have 6 independent stresses, right? What are those 6 independent stresses? You have 3 different shear stresses, right? And 3 normal stresses. So 3 normal stresses plus 3 shear stresses, then you get 6 independent stresses. Okay, so this is the stresses in the 3D domain. For the strain, how to calculate the strain? We have normal strain and also we have shear strain, right? So the in this XY coordinate system, in this 2D coordinate system, let's start with a 2D coordinate system. You have normal strain in the X direction, also in the Y direction, right? So the normal strain in the X direction will be the partial derivative of U, which is the deformation in the X direction, over partial derivative of X, okay? So that's the deformation over the X. The normal strain in the Y direction, this is the partial derivative of V, the deformation in the Y direction over Y, okay? So those are normal strain. So if the V, for example, the V, which is the deformation in the express the deformation in the y-axis, right? If the V is a function of not only y but also x, then you will have this shear stress, not the shear stress, the shear strain, which is calculated based on this shear stress, the shear strain xy based on the angle deformation. Okay, so that is calculated based on the partial derivative of v over x. This is a deformation in the y-axis actually, plus u partial derivative u over y. Okay, so this is the fundamental for the calculation of the strain. And to be clear that those displacements u, v, which is in the x direction, y direction, they can be a function of x, y, and z, right? If we consider the third domain, and that's why you may have a shear strain, right, in the x, y, y, z, or x, z. And w usually shows the displacement in the z direction, right? Similarly to this one, you will have, let me write down, okay, it's shown here. You can calculate the shear strain in the YZ, shear strain in the ZX, and normal strain Z, right? In a similar way. The shear strain YZ, that is equal to partial derivative of V, the Y direction, right, over partial derivative of Z, plus partial derivative of W in the Z, the displacement in the Z direction over partial derivative of Y. So that's a pattern. And the normal strain in the Z-axis apparently is the displacement in the Z direction over the partial derivative of Z. So now we know how to calculate the strain and stress in the 3D domain, right? So in order to, so for 3D domain, if you want to show your strain of your a 3D 3D object, right? For example, you have a 3D object. And if you want to show the strain, you cannot, you have to express the strain in 3 direction, normal strain in 3 direction, and also shear strain, right? 3 shear strains. So actually, if you want to show the strain, you need to express 6 strains, right? And you can write the strain in a format of a matrix, right? Similarly to the stress, right? This is also 6 elements matrix, right? So we know that stress and strain have the relation, right? Hooke's law. Stress can be easily calculated based on Young's modules and strain, right? For the 3D domain, this is in 1D domain, right? One dimensional. For the 3D domain, you also have this similar to this relation, right? So if we find out, apparently this is column vector, right? It's 1 by 6. This is 1 by 6. No, 6 by 1, sorry. Six row. Let me see. One column. 6 row. 1 column. All right. So you will have the relation of strain and stress matrix. We'll have another matrix, right? 6 by 6 matrix as a relation, as a factor for between those two, right? So we call this matrix, 6 by 6 matrix, as the elastic moduli. So for a body that is linearly elastic and small deformation, the stress strain stresses and strains at a point are related through the 6 simultaneously linear equation called Hooke's law. So this is derived. No, I cannot say it's derived. It's actually similar to this equation. It's made by this equation, right? It's a combination of this equation. If you expand them, right? So for linear isotropic material, this is a really strong assumption, right? It's a linear material and also isotropic material. It's a isotropic material. So for this isotropic material, in the 3D domain, the stress and strain, the relation between strain and stress will be expressed by this elastic moduli, right? So if you expand this, right, you can get the strain, normal strain of X equals to this row times this column, right? So will be 1 over E right? Minus balance ratio E Y minus balance ratio E Z, right? So this makes sense, right? If you only have a stress in the x direction, this can be easily calculated based on the Hooke's law, right? So what are those two parts? Those two parts is based on the Boltzmann ratio, right? If you have the strain, if you have the stress applied in the y-axis, you, based on the Boltzmann ratio, Boltzmann effect, you will, this stress in the y-axis, y direction, also contribute to a strain in the x direction, right? Similar to the stress in the z direction, similar to this case, right? So this makes sense. This is the expansion of this first row, right? So the strain in the y direction, normal strain in the z direction, they all make sense. So about the shell strain, shell stress, shell strain and shell stress. For the shell strain YZ, let's see what is shell strain YZ right here. YZ here is the fourth row equals to this times this strain, this column, right? So that would be 1 over G times shell stress YZ, okay? So this shell strain only contributed by the shell stress in that direction, right? So the G is the shell modulus, right? So this makes sense for the isotropic material. So you please don't be afraid of this large matrix, right? It's only a combination of 6 equations of the stress and strain, right? You can write this. You can write 6 individual equations in this way, but to make your life easier in the future, you should write it in the matrix format, right? So that's much easier. All right. So here we only have you only have, once you know this Young's modulus, right, of the isotropic material, Young's modulus, Boltzmann ratio, and shell modulus, you know this elastic moduli, right? If you can also get the relation between the stress and strain. So that the previously is the strain for the equation strain to the stress. So you can find out the relation based on, you can find out the stress based on the strain. Just take the inverse of this matrix, right? Then you get another matrix. This one becomes a little bit more complicated, right? But still manageable. And see, this matrix is also made of Young's modulus, Boltzmann ratio, and the shell modulus, right? The shell modulus can be calculated based on the Young's modulus and the Boltzmann ratio. So this elastic moduli of the isotropic material, it's actually only have 2 variables, right? One is the Young's modulus, the other one is the Boltzmann ratio. So if you know those 2 variables, you know the relation between stress and strain. Okay. And once you know the stress and strain, in the solid, right? in a solid and deformable elastic bodies on the load, the work done by external load is stored as the recoverable strain energy. So it's an elastic deformation. So the strain energy stored in the body per unit volume is calculated based on stress and strain. Okay, so the work equals to 1/2 strain times stress, normal strain times normal stress, normal strain times normal stress in x, y, z direction, and shell stress times shell strain. Now those three different units. So that's the strain energy you can calculate based on strain and stress. Okay? So this is really useful in the future when you, for example, when you do the finite element analysis, right? You can derive the equations based on the strain energy. So for this lamina, we want to laminate, right? This laminate made by lamina. We want to find out the 3D stiffness and the compliance matrices. Okay. Sorry, I haven't met. I didn't mention that the compliance matrix and the stiffness matrix. Okay. So what is the compliance matrix? Compliance matrix actually is the relation between the strain and stress. So if you have this relation really in a simplified way, right? Strain equals to compliance matrix S times stress, okay? So this is a more simplified equation. And this is a general material. If you have a crazy material, a really general material, you have this compliance matrix S. This is quite independent to other. Those values are independent, right? But it should be symmetrical matrix. So if you express the stress based on the strain, you get the stiffness matrix, which is usually expressed by the matrix C. Right? Simplified version will be stress equals to stiffness matrix times strain. Right? So don't get confused, because here usually people use the matrix S for the compliance matrix. For the stiffness matrix, we have the matrix C for the stiffness matrix. Vice versa, I think it makes more sense. So here, how many unknowns? Right? It's 6x6 matrix. So 36 element here, right? 36 constants. But all those stiffness matrix or compliance matrix, this should be a symmetric matrix. So if you have the symmetric matrix, these values, those constants, should be equal to each other, right? So that reduces the constants to 21 independent constants. So you have 21 independent contents for general material. It's still a lot, right? So for a special case, for general case, right? If you really have a 21 independent elastic constants for that compliance matrix and stiffness matrix. I can't help with that right now. This is called a anisotropic material, right? So it's the most generous material. For isotropic material, you'll see I've shown you that this compliance matrix before, right? So if you write in this format, you'll see you only have two independent value, right? S11, S12, and this is G, right? This is G. For the compliance matrix, of the isotropic material, you also have two independent values, right? So this is S11, S22, S33. Oh, so this is the same. For stiffness matrix, based on that format, you have C11. This is actually C22, C33, right? So you also have two different values. Those three parts, actually those 6 values are the same, and those 3 values are the same. Right, those 3 are same values, right? And the rest, these 6 are also the same, and those are G, value G. And the value G can be calculated based on C11 and C12, right? Okay, so that's the case for isotropic material, which I have shown you before. For more complicated case, which is the orthotropic material. So what is the orthotropic material? So for orthotropic material, they have material symmetric axes, 3 symmetric axes, and that material will have same properties along compared in between that axis, right? Between that symmetry, they have the same material properties. So if that material has a 3 mutually perpendicular planes of material symmetry, the 3-dimensional matrix will have a 9 independent elastic constants. So you have Young's modules in 1, 2, 3 direction, and shear modules you have 3 different shear modules, and also 3 different Boston ratio. So that's why you have 6. No, not 6, 9, right? This is 9. You have 9 independent elastic constants. Okay, so the compliance matrix expressed in this way, you have C11, C22, C33, C12, C13, and this is symmetric, right? C44, C55, C66 is shell modules, right? So the compliance matrix also is also expressed in the similar way. And if you try to calculate this S11, S12, S13, you can simply expand it, right? And find the relation of this normal strain based on the normal stress and shell stress, right? So currently here, it's not this normal strain in the one direction, but nothing to do with shell stress, right? So you can calculate in that way, right? So it's pretty simple calculation. I can expand this for you a little bit. So here, for the first row, you have strain in the one direction calculated based on the Young's modulus E1, right, in the one direction times positive ratio 1, right? So this makes sense, right? And also the second one is a positive ratio 1, 2 over Young's modulus 1 stress in the two direction, right? Minus positive ratio 1, 3 Young's modulus 1 in the three direction. Okay. Right. So this is the case for the orthotropic materials and the equation for the compliance matrix. Stiffening matrix is the inverse of that matrix, right? So you can get that from the inverse of that matrix. This becomes a little bit more complicated compared to isotropic materials because of this increasing unknown fact independent values, right? Independent constants. So yeah, so this is the Stephen matrix C. So for our lamina, a more general case is not only orthotropic. So usually for most of our lamina, right, one layer ply lamina is their orthotropic material. But for some well mixed, well dispersed unidirectional reinforced unidirectional lamina, it can be a transversely isotropic material. What does that mean? That means you have, because this ply is well dispersed, these fibers are well dispersed. So in the plane of 2, 3, right? In the plane of 2, 3, if you have a cross section of 2, 3, right? So this is a cross section of 2, 3, right? So in the 3 and 2 direction, you actually have same. This is the 2 direction, right? This is the 3 direction. In those 2 direction, you can consider this is isotropic material, right? If you average these physical properties. So the Young's modulus, for example, the Young's modulus in the 2 direction will be the same as 3 direction, right? So this is the plane, this is called the plane of isotropy. So this material is considered as transversely isotropic material. But for this one, for this material, for this lamina, those fibers has to be arranged pretty. So they have to be arranged without the directional dependence, right? They have to be arranged in a way that is the same in the 2 direction and 3 direction. So for that this is a bit stronger definition compared to this orthotropic material, right? So in that way, for the 2-3 parts, okay, so this 2-3 parts is the isotropic material, right? So for the 2-3 parts, it's more isotropic material properties, actually, right? So this is the same as the compliance matrix for the isotropic matrix. Right. And also the shell strain 3-1 and 2-1, right? So they should be the same, right? Because the 2 direction and 3 direction are actually pretty much the same. So that's why you have this S55, SF5 here. That's the same. So here you have less independent constants in the transversely isotropic material. You can count how many independent constants here. So stiffness matrix also got simplified here, especially this area and this area. So in summary, if you we mostly review the stress-strain relation in the 3D domain, right? We want to find out relation between stress and strain in the 3D domain. So we know there are 2 matrices, which is the compliance matrix S and the stiffening matrix C, right? So this is compliance matrix, and the stiffening matrix is actually the inverse of the compliance matrix. Right? So we want, this is key to express the relation of your stress-strain relation, right? So this stands for, this is a good expression of your physical properties, right? And for a general case, a general material, for anisotropic material, you have 21 independent constants for the compliance matrix and the stiffening matrix. While if you have an orthotropic material, you have 9 independent constants. If you further, if you have one isotropic plane, right? This material becomes a transversely isotropic material, which can be the case for all of lamina. Then you have 5 independent unknowns, independent constants. And for most special case, which is the isotropic material, you only have 2 unknown, 2 constants. But that's not the case for our unidirectional lamina, right? For our unidirectional lamina, it's more of a case for the transversely isotropic some case is we have to consider it as the orthotropic material, right? So that's a summary for today's lecture. We will cover more in depth in the next lectures. Thank you. So as for the final paper, the review paper, I will send out a notice on the deadline and what the requirements and a few papers that you can learn from. Okay, so please let me know if you have questions. I also will set up a office hour time on Zoom, and you can feel free to join me if you have questions. And the link to join the Zoom will be posted on Canvas. Thank you. Bye bye.